Good morning, all. Our speaker has joined us, so let's start the program for today. A very pleasant good morning to all of you, and welcome to today's faculty development program on advanced mathematical techniques in engineering and technology, organized by Department of Mathematics, Maharshi University, Rohtak, sponsored by AICTE ATAL. I, Dr. Kumar, Organizing Secretary of this FDP, on behalf of the Department of Mathematics, welcomes you all present here. Now I would like to request Professor Rajeev, Coordinator of FDP, on the board, welcome our participants and our eminent speaker, Professor R.K.Sharma, sir. Over to you, sir.
A very good morning to each and everyone on the day of 8th October 2021. First of all, I welcome the ICT training and learning for sanctioning the online FDP, the Department of Yes, I'm audible. Okay. Thank you. Sorry, in my system. So, welcome AI training and learning for sanctioning the mathematics, and also I extend my thanks for very well hosting the inaugural ceremony of FDP. You see, this FDP was also by ATAL Academy, not for our department, but in addition, he was there. That was commencing from today only, and that are being organized by different institutions across the country. Now, we feel proud and honored that our Vice Chancellor, Professor Rajveer Singh, was the chief guest of this online. And we are very grateful to Professor Rajveer Singh, Vice Chancellor of the University, for sparing his valuable time for inaugurating this FDP. On behalf of myself and the organizing committee, I extend thank you to the Honorable Vice Chancellor for the encouragement and the motivation for organizing such programs from my university. I also welcome the distinguished and speakers from several premier institutions in India and abroad who have given their kind consent to share their knowledge and enlighten the participants. Today's distinguished speakers, I welcome him, the Professor R.K.Sharma, Department of Mathematics, IIT Delhi. Special Professor Renu Chugh, former Director of Research and former Head, Department of Mathematics and Rohtak. Professor C.B. Gupta, Director IQAC, the North Camp University Gurugram, who are the eminent speaker for the today's session. I welcome all academicians, scientists, teachers, faculty members, research scholars, and students who are on the board from several places in India, and they are the participants. It is my proud privilege to extend heartiest welcome to all of you in the online FDP during this COVID-19 pandemic situation. through the System meeting platform. It is my pleasure to apprise you of the board that this FDP has received overwhelming home from a large number of participants across the country. That is from various institutions that belong to 30 states and city of India. Participants are elected to have maximum of 200 participants by the AICD. And moreover, the highest representation is from Tamil Nadu. There are participants 35. Then from Telangana, there are 23 participants from Telangana. Maharashtra, there are 21 participants from Maharashtra, and then my state, Haryana, it has 20 participants, and Uttar Pradesh has 70 participants. I welcome you all the participants from their institutions and home who have joined and shown their trust in our activity. I welcome also all of you on the board from board of my heart. I am very much sure that this FDP will enhance knowledge and fruitful sharing on the topics related to advanced mathematical techniques and engineering and technology. My best is each and everyone. Now let me invite the speaker of the first session of the day, respected Professor R.K.Sharma, who is from the Department of Mathematics, IIT Delhi. Let me go through just a brief profile of respected Professor R.K.Sharma. Professor R.K. Sharma is going to deliver his talk on uses of algebra in Unix. Professor R.K. Sharma is a professor of mathematics at the Institute of Technology, Delhi. Earlier, he was the faculty of mathematics at IIT Kharagpur. He has been teaching UG and PG classes for more than 50 years. He has guided more than 34 years in physics and 18 MTech projects. He has published more than 150.
Good morning, sir.
He has participated in several conferences of the world, including the International Conference of Mathematicians in 1990 in Switzerland. He has also traveled widely throughout the world, delivered talks. He was a postdoctoral fellow in Germany. Several students working under him and working into forms of projects also. The area of interest of Professor R.K. Sharma is algebra and cryptography. I hope all of you have of the knowledge that Professor R.K. Sharma is going to share for this particular technical session. And I hope that each one of you will have an interest in algebra and cryptography and going to speak on the uses of this in technology. So have a good day. I welcome once again all of you and thank you for joining us and hope I will be there for 5 today. What weather will learn the thing and have a kind of knowledge. Thank you very much. So I welcome Sir R.K. Sharma, the board, to deliver this start. Thank you, sir.
नमस्कार राजीव जी,
I'm audible?
आप मुझे सुन पा रहे हैं आवाज?
Yes, sir.
तो राजीव जी पुनः नमस्कार और सभी देवी और सज्जनों को मेरा नमस्कार, प्रणाम। ये मेरा परम सौभाग्य है कि महर्षि दयानंद विश्वविद्यालय समय समय पर यह सुअवसर प्रदान करता रहता है कि आपके समक्ष कुछ वार्तालाप किया जा सके। और बहुत बार मैं वहाँ आया और हर बार मेरी इच्छा भी रहती है कि वहाँ आए, आपसे मिलें और अन्य गणितज्ञों और वैज्ञानिकों से मिलें और वार्ता का आनंद लें। किंतु कुछ समय से, जैसा कि हम सभी जानते हैं, ये कष्टकारी समय रहा और हम एक दूसरे से उतने अधिक नहीं मिल पाए जितना मिलना चाहते हैं। पर फिर भी जितना भी संभव हो सकता है, आज के युग में काफ़ी कुछ तकनीक ने हमें इस बारे में सहायता की है। तो अब हम एक दूसरे से भले ही ना मिल पाए, लेकिन ये है एक दूसरे के समक्ष तो होते ही हैं, भले ही वो एक दूरी से हो। कभी कभी इसमें कुछ दिक्कतें भी आती हैं, जैसे अभी नेटवर्क की प्रॉब्लम में थी, मेरी तरफ से भी थी. तो एनीवे, सो good morning to you all, ladies and gentlemen. It's a great pleasure to be with you once again. And as I mentioned that I have always been fascinated by MDU and its staff, faculty, and all the people. And they have been very kind and generous to invite me time and again. It's a great pleasure, great honor. I always wanted to be one thing in life is that to be young. And as you know, being young is not always that easy. So what I try to do is that I wish that I be with the young people, and younger the better. And that is why I travel very often, as much as possible. Now, of course, is through internet only. And then communicate and try to know what is it that the youngsters need about mathematics, training, learning, and teaching, and so on. And I wish that I could extend whatever way I could, whatever a little bit I have done or I take interest in, to impart to those youngsters. And since in this meet, the trainers themselves are there. Basically, they share a greater responsibility in passing on to the young generation the message that India had done great in mathematics and all other sciences as well. We all know that this is true. This is true in all regions, languages, and literature that has been accepted worldwide, that mathematics is the queen of all sciences. And in our literature in Vedas also the same thing has been said. Yatha shikha mayuranam naganam maniyo yatha Vedanga shastranam gaditam murdhani. And being Indian, I hope that you are expert in Sanskrit, but still for my satisfaction, I would like to tell this in a simple language, is that Yatha Shikha Mayuranam, as on the head of the Mayuranam peacock, there is a crest, there is a crown sort of. Yatha Shikha Mayuranam Naganam Mani. The same way on the hood of the cobra, there is a symbol, we call it jam, mani. Tadavedanga Shastranam, the same way. On the top of all science and mathematics, it's on. That is the address of mathematics. When we say that address of mathematics, that means that if you look for a good science, good technology, good engineering, or anything that you aspire to be good at, then you must be good in mathematics. That is the basics, that is the foundation. So if the foundation is strong, naturally, whatever you build on will be stronger. And this is not just a saying, this is time-tested theorems. So, you know, see, why idioms and phrases are so important in life? Because they are time-tested theorems. People keep on saying for observations that they make, and then it is found true. And that's how, although these are not well documented the way the other literature is, but then it is more so often used freely in the society that has become idiom phrases that very often people would like to pass on for the same phenomenon. Well, saying so, what I mean to say is that the importance of mathematics has been recognized world over for the growth of all subjects. Now, when it comes to mathematics, it's a world in itself. Naturally, mathematics seems to live in a different world. And that is mathematics that is so wide, so vast, and so many subjects have been born out of it that you really cherish, you really enjoy. And when it comes to mathematics, when does it enter into the life of a child? As soon as I believe the child is able to say mommy and papa, the next thing that mother teaches, of course, the mother is the first teacher of the child who teaches how to say mommy, papa, and after that, what? So that begins with that the mother tries to teach the child how to count. So 1, but the child never says 1. And see the patience of mother, that she is determined to teach the child 1. And now very modern methods are also used. So what is a modern method? Modern method is that you try, you repeat, and you believe that child will repeat after you, but nobody does. So what do? Then you bring out something which child might like, and nowadays chocolates are the thing that if you show a chocolate, the child will start bouncing on that. So you bring a chocolate and then you say, okay, 1. The child tries to grab the chocolate but never says 1. And therefore, you don't give because you don't want the chocolate should be wasted just without learning anything. So you again say 1, and the child again tries to grab the chocolate. And when you say it 4th time, the child says 1. And then you give the chocolate. So what happens then? You are happy because you have 1. You have 1 because you have taught him 1. The child is happy because the child has got 1 chocolate. The next day you come with 2. And then you say 2. The child blinks, tries to grab again. You don't give. When you repeat the 2nd or 3rd time, child says 2, and you give away the 2 chocolates. You are happier now. Child has learned 2 also. Sorry. So then next day you come with 3, and then you teach him 3. Once you say 3, he immediately says 3, and now he doesn't wait anymore. The moment you come next day with 4, he says 4, and so on and so forth. One day you come with a box of 10, and the child says 10 immediately after you have said it 10. Well, look at the pocket now. 1 chocolate costs 20 rupees. And how much it has costed you when you have taught him 1 to 10? Just imagine. 1 to 10. How many chocolates you have given away? Already. 1 on the first day, 2 on the second day, and so on. These are 45 chocolates. 55 chocolates. How many you have given? So you add 1, 2, 3 up to 10. So 10 into 11, 50. And then you can see 1 chocolate costing you 20. Is 1,100. 1,100 you have spent just in teaching the child the counting, how to count 1 to 10. It's a costly affair. So what do? You say better not teach 11. Rather teach him how to count reverse. Right? So then you remove 1 chocolate, next day you say 9. And so on and so forth. 8, 7, 6, 5, 4, 3, 2, 1. Every time you take away 1 chocolate, child is angry and angry. So when you have come finally with the bare empty palm, you have nothing in your hand, and you say 0. Child never says 0. You try this. No wonder people didn't think any importance of 0. And it took quite a lot time, nearly a century. 0 was invented. And we take pride in it. Remember it. That our past is so glorious that 0 was invented in India. Of course, 550 BC. So India has done great in mathematics, astronomy, and so on and so. Yet, we haven't been able to propagate this to the masses, to the young children, that what our ancient literature consists of. What does it contain? It's our responsibility to make them aware and, of course, encourage them to do nice mathematics. as expected. Of course, the child is the father. Man, what does it mean? That we have a lot of things to learn from each other. Such a fresh mind has so much energy, so many innocent questions. Sometimes you don't have answers to them. And by trying to answer them, history is there to observe them. Great inventions were done. Child prodigies, of course, are in abundance. How to add natural numbers 1 to 100 is the story. Was when Carl Friedrich Gauss was a young kid in his school and his teacher wanted to relax and gave this problem to the class that add 1 to 100. No sooner the teacher gave the problem, this bright young student says the answer is 50. What is 50? 50 is the answer. He said, how come? And that's how he narrated that he wrote 1 to 100. And then in the descending order, 100 to 1. And every time added 101, 101, 100 times. So 100 into 101. Since the job was done twice and therefore divided by 2. So 100 into 101 divided by 2, 50 into 101, that is 50, 50. And that was the answer. And even today, this is the same method, how to add the counting numbers. 1 to n, that n into n plus 1 by 2. Thing is that there have been so many bright young mathematicians that they made history. Another, of course, Evariste Galois. He died very young. But whatever he did, he didn't live beyond 20 years, but whatever he did is known after his name, Galois theory. And we teach the students in their masters only a glimpse of that. The same way, we also are proud to have Srinivasa Ramanujan. India has produced as a great mathematician of the modern era. He too didn't live long, 33 years just. But what he did, people are still working on that. Even the rough notebooks that were known as the lost notebooks, 2 in number, people are still working on. There have been many challenges in the life of those people. So we don't have to be cowed down by the problems, hardships, and so on. The life story of these great mathematicians tell us that we must stand up. We must stand against all odds and must contribute whatever way we can and must always aspire to look beyond. Since Rajeev was asking me to say a few words about linear algebra, and of course, when it begins mathematics after counting numbers, addition, subtraction, of course, first addition, then multiplication, and then subtraction, and then division as the reverse process. Then the next thing comes factorization, and then comes how to solve equations, and so on. Very early mathematics sits beside us and starts changing the life. It's too vast to talk about all. Naturally, he asked me that you must say something about linear algebra and its applications. Everything is quite vast. So in this talk, we shall only talk about the preliminaries and as far as possible how to introduce the subject, that is the main objective, is from the young student's point of view. So I would share a little of the slides so that you can also read yourself and enjoy at the same time. Share. So, Rajeev, tell me if you are able to see the screen and are you able to hear me?
Yes, sir, it is visible.
Yes, sir. Yes, sir. It's visible.
Okay, nice talking to you. Actually, it becomes a monologue when I don't see people and when I don't see them reciprocating. Basically, I love participation from both sides equally. That gives great pleasure. Anyway, whatever is that, because if all start talking, then also is not a good thing. So this is basically just an introductory sort of thing about linear equations, matrices, vector spaces, and so on. There are several ways of introducing a subject. So some says, okay, linear algebra is the study of lines, or anything that falls in line is the study of that, and can be represented in terms of those concepts. Well, it is quite natural when the student is in class 6th that what he has been learning was that far was only arithmetic. The mathematics then splits into two branches. So one is arithmetic is now changed to more towards symbols rather than numerical values, and the other one is to enjoy drawing something. That is called geometry. Geometry very soon splits into two parts. That is how to construct, how to draw, and the other important, equally important part is to prove what you have drawn is correct, the proofs. But then when it starts as soon as you put your pen or pencil on the paper and you make something like dot, and then you say, what is it? Oh, it's point. And then soon it starts, okay, point. What is a point? What is, when you just scribble a little, then you say line. What is a line? That is the next question. And so on and so forth. So a great deal has been spent by mathematicians. The whole problem with mathematicians is that they are perfectionists. They want a definition, a statement that should clearly, without any ambiguity, must define with minimum words. That means nothing extra should be put up in the statement. And no matter, even after 1,000 years, there shouldn't be any contradiction to this statement. Not that you change the theory of it. So that is what is very important in mathematics, is the definition. So a great deal was spent on defining what is a point, what is a line, and so on. Coxeter said that you have to begin somewhere. So you have to start at some point of time assuming, okay, this is the case. So some postulates have been framed. So that's how the Coxeter said that you assume you know what is a point, what is a line. For example, that, okay, what is a circle? A circle is the locus of a point that remains equidistant from a fixed point. Now this fixed point is called the center of the circle, and this fixed distance is called the radius. And then the student jumps and says that, okay, sir, what is a point? Fine, a point in a circle with zero radius. Great. So what have you? My home is in front of the temple. Temple is in front of my home, and where the two are facing each other. So have you taught that how to reach your home? No. This is something called like zero knowledge protocol. That you impart zero knowledge, but you make people believe you are a solution to their problems. So postulates have to be there because time and again you try to find out the definition and then remove that this is no more a postulate. But till then, they have to stay, and they have stayed since Euclid. It's time. In 13 volumes, Euclid did a wonderful job of this defining. And Coxeter took from that. Coxeter, HSM Coxeter, Harold Scott MacDonald Coxeter, was a British born mathematician who settled in Canada. A great geometer. Several books by him, including the plane geometry, projective geometry, and so on, and of course the bed geometry and groups and so on. Great literature. So I said, okay, I assume that postulates are there. There are other things that somehow you can, instead of drawing on the page with the line, assuming what you know, what is a straight line, then how to represent the line in the form of an equation. That means that there are two statements, in between there is an equal to sign. When these are mathematical statements, they are equations or identities. That is true always. So there are several ways of introducing a subject. Of course, we shall prove for this second. So linear algebra is the branch of mathematics concerning linear equations, linear mappings, and the representations in vector spaces and through matrices. Linear algebra is central to almost all areas of mathematics. It is, for instance, fundamental in modern presentation of geometry, including defining basic objects such as lines, planes, rotations, and so on. And in fact, the classification of conics from their equation, that whether the conic represents a pair of straight lines or it represents parabola, hyperbola, ellipse, or a circle, it's the linear algebra that decides rather more comfortably. So it's used in most sciences and fields of engineering because it allows modeling any natural phenomenon and computing efficiently with such models. Let me give a very brief history of linear algebra and matrix theory. So the study of systems of linear equations first were introduced by the Babylonians around 1800 to 2000 before Christ. So around 4,000 years ago, the people of Babylon knew how to solve a simple 2x2 system of linear equations with two unknowns. Around 200 BC, the Chinese published that 9 chapters of the mathematical art, and they displayed the ability to solve 3x3 system of equations. The simple equation of the form ax plus b is an ancient equation and is a very ancient question also that was worked on by the people from all walks of life. The power and the progress in linear algebra did not come to fruition until the late 17th century. For solving of a system of linear equations, Cardin constructed a simple rule for two linear equations with two unknowns around, say, 1550 AD. Cardano or Cardin, interesting and colorful personality, of course, published the mathematics book Ars Magna. And in this book, Cardano with Tata first used the numbers which are known as complex numbers. Lagrange used matrices in his work on the optimization problems of real functions around 1750 AD. Metric systems, some of mathematicians consider Lagrange as the founder of metric system, was used widely in the context system of linear equations. Also, determinant concept was used by Gauss and Dayanand. Gauss formulated this set of errors to be minimized as a system of linear equations. In ancient China before Christ, it was used different ways of solving the system of linear equations. These solution methods were not fully different to each other. For some of them could be used only for 2 or 3 equations with the same number of unknowns. Also, ancient Chinese made some correlations between the number of equations and the number of unknowns for unique solutions and more than one solution as well. According to some authors, there are many examples, applications, problems, and their solutions in the old textbooks. The introduction and development of the notion of a matrix and the subject of linear algebra followed the development of determinants which arose from the study of coefficients of systems of linear equations. Leibniz one of the two founders of calculus, used
Excuse me, sir. Sir, your voice is not audible.
as the maxima and minima of multivariate functions. This method is now known as the method of Lagrange multipliers. In order to do this, he first required the first order partial derivatives to be 0, and additionally required that a condition on the matrix of second order partial derivatives hold, like he said. This condition is today called positive or negative definiteness, although Lagrange did not use matrices very explicitly. Gauss developed the Gaussian elimination around 1800, and used it to solve least square problems in statistical computations. And later, in computations to measure the Earth and its surface, the branch of applied mathematics is basically concerned with measuring or determining the shape of the Earth or locating exactly points. The statistical science. On the Earth's surface is called geodesy. Even though Gauss's name is associated with this technique for successively eliminating variables from the system of linear equations, it appears from the Chinese manuscripts from several centuries earlier have been found that explain how to solve a system of three equations in unknowns by Gaussian elimination. For years, Gaussian elimination was considered part of the development of geodesy, not mathematics. The first appearance of Gauss-Jordan elimination in print was in a handbook on geodesy written by Wilhelm Jordan. Many people believe, and of course is incorrect, they assume that the famous mathematician Camille Jordan is the Jordan in Gauss-Jordan. For matrix algebra to fruitfully develop, one needed both proper notation and proper definitions of matrix. Both needs were met at about the same time and in the same place. In 1848, in England, J.J. Sylvester first introduced the term matrix, which was the Latin word for bone, as a name for an array of numbers. Matrix algebra was nurtured by the work of Arthur Cayley. In 1855, Cayley studied compositions of linear transformations and was led to define matrix multiplication so that the matrix of coefficients for the composite transformation is the product, or the composition ST is the product of the matrix S times the matrix of. They went on to study the algebra of these compositions, including matrix inverses. The famous Cayley-Hamilton theorem, which asserts that a square matrix is the root of its characteristic polynomial, was given by Cayley in his 1858 memoir on the theory of matrices. The use of a single letter A to represent a matrix, as is very common today, was crucial to the development of matrix algebra. Earlier in the development of the formula, the determinant of AB, the product is the product of their determinants. The determinant AB is equal to determinant A, determinant B, provided a connection between the matrix algebra and the determinants. Cayley wrote, there will be many things to say about this theory of matrices, which would, it seems to me, precede the theory of determinants. Mathematicians also attempted to develop of algebra of vectors, but there was no natural definition of the product of two vectors that held in arbitrary dimensions. The first vector algebra that involved a non-commutative vector product, that is V cross W, and that need not be equal to W cross V, was proposed by Hermann Grassmann in his book Ausdenmühl's Thread, 1844. Grassmann's text also introduced the product of a column matrix and a row matrix, which resulted in what is now called a simple or a rank 1 matrix. In the late 19th century, the American mathematical physicist Willard Gibbs published his famous treatise on vector analysis. In that treatise, Gibbs represented general matrices, which he called dyadics, as sums of simple matrices, which Gibbs called dyads. Later, the physicist Dirac, Dirac, Paul Dirac introduced the term bracket for what we now call the scalar product of a bra, that means a row vector, times a ket, the column vector, and the term ket bra for the product of a ket times a bra. Resulting in what we now call a simple matrix. Our convention of identifying column matrices and vectors was introduced by physicists in the 20th century. Matrices continued to be closely associated with linear transformations. By 1900, they were just a finite dimensional subcase of the emerging theory of linear transformations. The modern definition of a vector space was introduced by Peano in 1888. Abstract vector spaces whose elements were functions soon followed. There was renewed interest in matrices, particularly on the numerical analysis of matrices after World War II. With the development of modern digital computers, John von Neumann and Harman Goldstein introduced condition numbers in analyzing round of errors in 1947. Alan Turing and von Neumann were the 20th century giants in the development of stored program computers. Turing introduced the LU decomposition of a matrix in 1948. The L is a lower triangular matrix with 1 on the diagonal, and U is an column matrix. It is common to use LU decomposition in the solution of a sequence of systems of linear equations, each having the same coefficient matrix. The benefits of the QR decomposition was realized over a decade later. The Q is a matrix whose columns are orthonormal. Orthonormal means they are orthogonal, and the norm is 1. Orthogonal means they are mutually orthogonal, mutually perpendicular. The inner product is 0. And norm is 1. And R is a square of a triangular invertible matrix with the positive entries on its diagonal. The QR factorization is used in computer algorithms for various computations, such as solving equations and find eigenvalues. As far as the applications of linear algebra is concerned, there is no subject which is untouched, which does not use linear algebra. So be it solving the system of equations, in fact, anything that can be modeled into a system of equations, the linear algebra is there. So for example, in electrical engineering, there are famous three laws, Ohm's law and Kirchhoff's laws, two Kirchhoff's laws, voltage drop and current laws. And so whenever there is an electrical network power distribution, and it returns to, therefore, a system of linear equations. So is linear algebra there? Linear algebra is there in economics. Linear algebra is there, of course, obviously in linear programming. What is linear programming? That you have a function which is to be maximized or minimized subject to constraints. And these constraints are in the form of inequations less or equal to 0, say for example. And the variables xi's are positive. So one simple way, that is your simplex method, is that you draw lines by replacing these inequalities by equations and then try to find out the feasibility. Of course, there are not many applications, so this itself is the subject called linear programming. I see that there are talks there today itself on transportation problem. So he will be telling more on application in linear programming. Then Markov chains. Of course, Professor Taneja will be talking about how linear algebra is used in Markov chains. You have applications, for example, and what not, I would say, anything that can be modeled. Most often it returns differential equations, a system of differential equations, and mostly it's a first order system of linear equations. If they are not linear, they are made linear by putting constraints. And once it is a system of equations, they are the first order linear differential equations. Then linear algebra is there to solve it. So there is some matrix whose eigenvalues and eigenvectors play a very vital role in solving such system of linear differential equations of the first order. Even higher order equations are converted into such systems. You have then, for example, applications in civil engineering, in measuring stress and so on, chaos, fractals, genetics, age-specific population growth models, harvesting of animal populations, of course, the least square models, curve fitting and so on, that started with the Gauss himself. Coding theory. What is a code? Code is, after all, a vector space over a finite field. And since this program is initiated by NU, where many people are working in coding theory, so I would not delve on that. Computer graphics. Reps and morphs. Many things. In economics, Leontief for economic models. Leontief was awarded, of course, Nobel Prize in economics. Games of history. Graph theory was born after Decomposition, but this problem, and Euler solved this problem by representing the problem in terms of a graph. As you know, a river and 7 islands connected by 7 bridges. So he made to represent this problem in the form of nodes and edges, the graph. And then how to represent the graph? is basically with the help of the matrix, the adjacency matrix. The whole theory can be handled using linear algebra. Linear algebra can handle your coordinate geometry, for example. What is coordinate geometry? Almost anything that you do, tomography, imaging, compressing, so almost everything. And when it comes to let us say cryptography, because I take little interest in cryptography, and there are matrix-based ciphers. And coding theory matrices are used to detect errors, of course, and generating matrices. And in cryptography, there are crypto systems, so they are known as matrix ciphers. So, for example, Hill cipher, shift cipher, Hill cipher, affine cipher, and visionary cipher. Visionary cipher could be treated as a block cipher as well as a stream cipher. In a block cipher, a block of fixed length every time is encrypted, while in a stream cipher, it's a continuous stream of plain text that is encrypted, and for that auto key can be used. So auto key can be generated and can be used for encryption. It's also interesting to observe something, say for example, in the ancient applications of linear algebra to cryptography, this.
Not audible, sir.
There is one thing. Hello, आवाज आ रही? Hello.
Yes, it is audible, sir.
Acha. So, and another interesting thing you can observe is that, for example, when you say a circle. So, as we all know that circle is the locus of a point that remains equidistant from a fixed point. And this fixed distance is called radius. Now, this fixed distance, and therefore there, what is a distance? So, when it comes to asking what is distance between 2 points, so one is that you just put a straight line between the 2 points and you measure by whatever way you can. But then just doing that, does it suffice to define distance? And therefore, distance has to be defined as satisfying certain rules and better done by norm. And inner product induces a norm. And naturally, you can define the norm to be the square root of the inner product u with u. The norm must satisfy that this is always non-negative and is 0 if and only if the vector is 0. And the norm of alpha times u is your mod alpha non u. And if the vector space is real, then of course this mod is just the positive value of that. In case of complex number, this is the absolute value. And it satisfies what you can call as triangle inequality. That norm of u plus v is less or equal to norm u plus norm. It also satisfies the Cauchy's inequality, that the absolute value of the inner product of u v is less or equal to the product of their norms. There are various examples of norms. The Euclidean norm is the most natural norm that comes from our notion of distance. So if the coordinates, say, for example, in a plane of 2 points are, say, x1, y1, and x2, y2 of P and Q respectively, in that case, the distance is the square root of this distance. So that is given in the form of that the square of x1 minus x2 plus the square of y1 minus y2, and this whole is the square root of this whole. And it satisfies all the properties. Then another interesting thing is that besides this Euclidean inner product on Rn, so that is say Rn if you are doing, so Rn means the set of all n tuples R cross R cross R. So say the tuple is given by say u1, u2, un, and each ui is a real number. The Euclidean inner product therefore for such two n tuples will be defined by say u1 v1 plus u2 v2 plus un vn, in case you are taking this as the real inner product space. In case of complex inner product space, that means the field is complex. In that case, this will be ui vi bar. Ui vi bar means the complex conjugate here and added I1 to n. Now, there is something very interesting that one can have is to associate weights, and that is called the weighted norm or weighted Euclidean inner product first. So, weighted inner product space in Rn, say for example, can be defined as so W1 U1 V1 plus W2 U2 V2 plus W1 U1 Vn. Now, these Wi's are called weights. You can see that this satisfies the property of being an inner product, where these weights Wi are positive real numbers. So what is the inner product here of U1, U2, Un with V1, V2, Vn with weights say W1, W2, Wn is the sum W1, U1, V1 plus W2, U2, V2 plus and so on Wn, Un, Vn. Now this particular example, you can take the arithmetic mean or average is of course is an inner product that you can check. Now weighted Euclidean inner product, if you define, now let us say if you take R2 over R and the weight say W1 is 3 and W2 is 2. So you can verify that 3U1 V1 plus 2U2 V2 satisfies all the requirements for this definition to become an inner product, and prove that. And you can then take the norm of with respect to these weights u comma u. So the coefficients here are 3 and 2 of u1, v1 and u2, v2 respectively. So this becomes quite interesting to note that when you have done this, and now you define that the circle is a collection or is the set of points, so say u, x, y, such that norm u is 1. So that is a unit circle. Now if this norm is Euclidean, so in that case this will be, say, u is xy, so this Euclidean norm will be x square plus y square square root of that. And when this norm u is equal to 1, this will represent the circle, unit circle, as we see centered at origin, x square plus y square equal to 1. But quite interesting thing will happen if you replace this Euclidean norm by a weighted norm. And if you define this weighted norm as the square root of, say, 1 by 9, x square plus 1 by 4 y square, as we have done this already, the 3u 1v1 plus 2u2 v2. And in that case, this norm u equal to 1 will give you the equation that is square root of x square by 9 plus y square by 4 equal to 1, and squaring both sides will give you x square by 9 plus y square by 4. Now x square by 3 square plus y square by 2 square equal to 1. Our understanding is that it represents an ellipse. So the unit circle with respect to this weighted norm becomes an ellipse. So you can enjoy also a lot of things using the linear algebra as such. Towards the end, we shall also talk about some ancient applications in mathematics, Vakale scripts, which goes back some 200 AD or so, that had some 70 scripts were there, and on that something was recovered as translated, and has interesting problems, and which can be formulated in the form of an system of linear equations, and has quite interesting solutions. Just briefly, I would like to talk about here. So as I said that we shall take the path of algebra to define equations, etc., rather than geometry. So a linear equation in the variables x1, x2, xn is an equation that can be written in the form, say, a1 xn plus a2 x2 plus a1 xn is 0, where b, this is b is equal to 0 here, and the coefficients a1, a2, an are real or complex numbers, and they are usually known in advance. So an expression of this form is called a linear equation. This subscript n may be any positive integer. So just simple example, 2x1 minus 7x2 is equal to minus 5 is a linear equation. 3x2 plus 4 times square root 5 minus 2x1 plus x3 is also a linear equation because it can be rearranged algebraically in the form as described earlier, and it becomes 8x1 plus 3x2 minus x3 is equal to 4 square root 5. However, the equation minus x1 plus 3x2 equal to x1 x2 is not linear because of the presence of the term of the form x1 x2. Another equation which cannot be linear is 2x1 minus the square root x2 is equal to 3. A system of linear equations or a linear system is a collection of one or more linear equations involving the same number of variables, say x1, x2, xn. Now, a system, for example, you can take 2x1 plus x2 plus 3.5, x3 10, and x1 plus x3 is 6. So it's a system of two linear equations as it contains two. Another example here, you have a system of three linear equations. Solving means what? A solution of the system of linear equations in n variables. So is a list of numbers that makes each equation in the system a true statement. When the values s1, s2, sn are substituted for x1, x2, xn respectively. An example, you can see that just now I have stated the same example. And here you can observe that 8, 1, minus 2 is a solution of this system, because when these values are substituted in this system for x1 and x2 and x3 respectively, then the equation simplified to 10 is equal to 10 and 6 is equal to 6, and that makes the true statement. So the set of all possible solutions of a system of linear equations is called the solution set of the linear system. So the same example when you do, you can see the solution of this linear system in R is given by this set 6 minus x3 minus 2 minus 1.5 x3 and x3, where x3 can be taken arbitrarily for all values of x3, real values of x3. Equivalent linear systems, so two linear systems are called equivalent if they have the same number of solution sets. For example, the system of linear equations 2x1 plus x2 plus 3.5 x3 and x1 plus x3 is equal to 6, and the system say x2 plus 1.5 x3 and minus 2 and x1 plus x3 is equal to 6 are equivalent because they have the same solution set, namely 6 minus x3 minus 2 minus 1.5 x3 and x3 being arbitrary. The solution set of a system of two linear equations in two variables. So just you have one example here. Consider these two equations. 2x1 minus x2 is 3, x1 plus 3x2 is 5. The graphs of these equations are lines which intersect at exactly one point, namely 2.1. A pair of numbers s1, s2 is a solution of this system if and only if s1, s2 satisfies both equations in the system. That is, if and only if the point s1, s2 lies on both of these lines. In this system, the solution set is the singleton set, namely consisting of one single ordered pair, namely 2, 1. Another example, you take 2x1 minus x2 is 3, minus 4x1 plus 2x2 is minus 1. Again, if you plot these lines and then you see that these do not intersect anywhere. Therefore, this system has no solution. This is so because a point s1, s2 is the solution of this system if and only if it falls on both lines. Consider the linear system of two linear equations in two variables. So say 2x1 minus x2 is equal to 3 and minus 4x1 plus 2x2 is minus 6. Now these coincide. That is, they intersect at every point on the line, and therefore this system has infinitely many solutions. So you can make a statement based on these examples that a system of linear equations has either no solution, exactly one solution, or infinitely many solutions. And you can have here examples. So 2x1 minus x2 is 3 and x1 plus 3x2. This is exactly one solution. Solution is 2, 1. Another example is that there is no solution, that we had already discussed, that the two lines do not intersect anywhere. And finally, we also had example where the two lines are actually coincident, and that has infinitely many solutions. So based on these, therefore, we can define consistent and inconsistent system of linear equations. So a system of linear equations is said to be consistent if it has either one solution or infinitely many solutions. For example, 1, it is consistent because it has exactly one solution. And The last example was also consistent because it had infinitely many solutions, but in between we had an example where there was no solution, and such a system of equations is called inconsistent. Representing equations, linear equations, and linear equations in n variables, namely say x1, x2, xn, in the form of a matrix, so is quite helpful. So if the equations are a11 x1 plus a12 x2 plus so on plus a1n xn equal to b1, second equation a21 x1 a22 x2 plus a2n xn equal to bn. And ith equation therefore would be ai1 x1. So this I is because of the ith equation. ai2 x2 plus so on plus ain xn equal to say bi. And finally, mth equation am1 x1 plus am2 x2 and so on plus an xn equal to bi. Now this what you do is interesting thing that you just retain these coefficients once you have the understanding that the xi's, where do they occur, because you have put them already. So if you just retain the coefficients and put them in a box so that they don't run away, so this would look like this. So this will be an array of elements a1 with the coefficients a1 to a1n in the first row, and like that, last row will be a1, a2, a1n. Now this particular array is called the coefficient matrix, or the matrix of coefficients of the above system of linear equations. And if you also include one more column, what is there after the equal sign, equality sign, then it has you have one more column. So the number of columns are now in +1, while the number of rows have remained the same. And rows, this new matrix is called augmented matrix of the system. An augmented matrix of a linear system consists of the coefficiental matrix with an added column containing the constant form. Constants are from the right side. The size of a matrix tells how many rows and columns are there. Augmented matrix has m rows and +1 columns. And so on. These observations you can have. Now, solving a linear system, the basic strategy is as follows. That use the x1 term in the first equation of a linear system to eliminate x1 term in the other equations. Then use the x2 term in the second equation to eliminate the x2 terms in the other equations, and so on, until a very simple equivalent system of equations is obtained. So important thing is that we reduce the system of linear equations by these simple operations which include three main forms, that is replace one equation by the sum of itself and a multiple of another, interchange two equations, and multiply all the terms in the equation by a non-zero constant. So these are called as the basic operations or elementary operations on the equations. Is basically to convert the given system of linear equations to a relatively easier equivalent system. Relatively easier means that we can hope to solve it easily. And the best system, of course, would be where each equation has only just one unknown and you solve it and you enjoy it. Take just one example and then things will be straight. So consider the system of linear equations, three equations here, x1 minus x2 plus 2x3 equal to 4, 3x2 minus 9x3 equal to 0, minus 2x1 plus 6x2 plus 5x3 equal to 13. The augmented matrix of this system is just retain the coefficients and drop everything else, including the equality sign. So it will have now here 4 columns and 3 rows. Columns 1 minus 1, 2, 4. That is the first row. Just keeping the coefficients. Second, here there is no x1, so coefficient is 0. 0, so 3 minus 9, 0, and minus 2, 6, 5. 13. This is the augmented matrix. Now keep x1 in the first equation and eliminate it from the other equation. That is what is our strategy to begin with. And for this, add 2 times equation 1 to equation 3. Equation 2 already does not have any x1. And the result of this calculation is that first equation same, second equation same as earlier. The third will have no x1 and it will reduce to 4x2 plus 9x3 equal to 21. Correspondingly, if you look at the corresponding augmented matrix now will be 1 minus 1, 2, 4, 0, 3 minus 9, 0, and 0, 4, 9, 21. Now multiply 2 by 1/3 in order to obtain as the coefficient for x2. This time because in equation number 2, the coefficient of x2 is 3. So make this coefficient as 1. So first and third equation are same. Second equation becomes x2 minus 3x3 is 0. And with the corresponding augmented matrix, just retain the coefficients and forget everything else. And now the same technique we shall apply with x2. That is in x2. Eliminate 4x2 from equation number 3. And for this, add minus 4 times equation 2 to equation 3. And the result of this calculation is what? First two equations same. Third will have no more x1 as well as x2. Third equation will be 21x3 is equal to x3. Correspondingly, you keep on looking at the augmented matrix. This is now 1 minus 1, 2, 4, 0, 1 minus 3, 0, 0, 0, 21, 21. And now again do the same thing that you make the coefficient here of x3 in equation number 3 as 1. So divide by 21 throughout. So equation 3 will be now x3 is equal to 1. By this time x3 is equal to 1 you already know. Corresponding augmented matrix is now beautiful than earlier. 1 minus 1, 2, 4, 0, 1 minus 3, 0, 0, 0, 1, 1. Eventually minus x2 has to be eliminated from equation 1. But it is more efficient to use the x3 in equation 3 to eliminate x3 from equation 1 and minus 3 from equation 1. And so if you get this, then corresponding augmented matrix also you keep on looking and continuing this, applying these basic operations and watching every time the equations as well as the corresponding augmented matrix, you will arrive at very soon on the system of equations which is so beautiful. That first equation is x1 is equal to 5, x2 is equal to 3, second equation, and finally third equation is x3 is equal to 1. And the corresponding augmented matrix is also very, very nice. So 1, 0, 0, 5, 0, 1, 0, 3, 0, 0, 1. So it shows that only solution of this original system, now the new system, which is equivalent to the original, to advantage is that they have both the same solution. It's 5, 3, 1. x1 is 5, x2 is 3, x3 is 1. However, since there are so many calculations involved, it is a good practice to check the work. So you just should verify that this really a solution or not. That means substitute for x1 5, for x2 3, for x3 1, and verify all the equations give you true statements. Now, what we have done is that we have applied basic operations on equations of the system. And we kept watching actually the corresponding augmented matrix. But if you just forget the equations and don't want to do the work twice, and you just keep on looking at the augmented matrix, then also you can do that. You can save a lot of effort. So then it reduces to 3 basic operations now on the rows that you are now performing. So replace one row by the sum of itself and a multiple of another row. Interchange 2 rows, and finally scaling, that means multiply all entries in a row by a non-zero constant. These are called elementary row operations. To remark here, we can observe that Row operations can be applied to any matrix and not merely to one that arises as the augmented matrix of a linear system. Two matrices are said to be row equivalent if there is a sequence of elementary row operations that transforms one matrix into another. Row operations are reversible. That means in any order that you make them, you can reverse this process also. For example, if two rows are interchanged, they can be returned to their original position by one, so more interchanging these two rows. And if a row is scaled by a non-zero constant c, then by multiplying the new row by 1 by c, that gives you the original row. Finally, consider a replacement operation involving two rows, say row 1 and row 2. And suppose that c times row 1 is added to row 2 to produce a new row 2. To reverse this operation, what should you do? Add minus c times row 1 to the new row 2 and obtain the original row 2. So equivalently, instead of doing the basic operations on the system of equations, you can do this on the rows of the augmented matrix. And from there, you can get back to the system. So row equivalent matrices will give you row equivalent systems. Existence and uniqueness questions will arise definitely. So is the system consistent? Then does it have at least one solution? And if the system has exactly one solution, is the solution unique? If the system has a solution, does it mean the solution is unique? So here are some examples that we had already seen also. And this example, once again, doing now this time doing just with the augmented matrix, and you keep on applying the elementary row operations till you arrive at this beautiful form. 1 0 minus 2 6 0 1 5 minus 5 0 0 0 minus 11. You can convert from here to an equivalent system. So this equivalent system will have these three equations, and interestingly, the last equation will give you 0 equal to minus 11, and that is an absurd thing, so it has no solution. So when you have converted the augmented matrix to its triangular form, you will be able to see if there is solution or not.
Excuse me, sir.
Boliye.
Yes, sir. Time is 1:15 now, so it's time for the QD session. If you can wind up in 1 or 2 minutes.
In 1 or 2 minutes, बिल्कुल जी आप 1 कहो मैं आगे मिनट में भी कहूँ.
Okay, sir.
ऐसी कोई बात नहीं. हाँ, एक चीज जरूर मैं शुरू में भी कहा था. Its applications to cryptography, as I said, that you can have to shift transformations to Hill ciphers and to affine ciphers and to the visionary cipher. So when you apply this on a block, then to shift this, so you can use the transformation as the encryption of a column. Now this column will contain the plain text as say x plus b, where b is a column again of the shift, say b1, b2, bn, modulo the size of the alphabet. Say for example, if the alphabet consists of only the 26 letters of the English alphabet, then modulo 26. Hill transformation means that you have encryption of x by ax. And this is now a column because n by n times n by 1. So you get a column n by 1. To get the solution from here, if A is invertible, you can apply A inverse on both sides, and that will give you x as A inverse y. Now, A inverse will definitely exist depending on its determinant. Is it prime or is it not prime to n, the size of the alphabet, the modulo n. So if it is relatively prime to that, this solution is unique, and you get the plain text, unique plain text easily. However, if it is not invertible, even in that case, so you can look at the GCD of the determinant and n and factor that out and can see that the new system reduces to a smaller modulo n by d, where d is the GC. And this system will have a unique solution, and then you will have d number of solutions, and from that applying extra knowledge or using all the solutions and discarding the solutions which do not satisfy the requirements, you get the solution. Then affine means this is ax plus b. So you first multiply and then you have shifted. Visionary cipher differs from the shift transformation in the sense that if the shifts are same, then this is simple shift transformation. But if the shifts keep on changing, that means b1, b2, bn, in that case, this is visionary cipher. And finally, this visionary cipher, as I said earlier also, this could be used as a stream cipher. The key could be, encrypting key could be auto-generated. And then it serves as a stream cipher. And since Madam Ji, you said 1 or 2 minutes, so I think I would like to say thank you at this moment for your kind attention, time, and concentration. So thank you very much from my side.
Thank you so much, sir. Now I request all the participants, if you have any query, then you can write in the chat box, or you can unmute yourself and then directly ask to the sir. All the participants, if you have any query, then you can ask now. I guess there are no queries at their end. So thank you so much, sir. Now I request organizing secretary of this program, Dr. Seema Mehra, to come on board for the thanks. Ma'am, over to you.
Thank you, Dr. Ekta. Thank you, sir, for giving your valuable insights on linear equation. Linear equation is in heart of linear algebra. Also, you explained all the central concepts of linear algebra very effectively. I think all the participants are benefited by your lecture.
आपका बहुत बहुत हार्दिक धन्यवाद और आभार इस अवसर के लिए। आशा करते हैं कि हम एक दूसरे से जल्दी ही मिलेंगे।
Thank you, sir.
जी नमस्कार।
Sir, thank you very much, sir.
जी
We are blessed that you are here.
ये तो आपका मैं कहूँगा आप याद करते हैं, सेवा का अवसर देते हैं, हमें अच्छा लगता है, बहुत अच्छा लगा। देखिए जल्दी ही जो है आशा करते हैं मिलेंगे।
Precious time to us.
नमस्कार।
Dear participants, now we will take a lunch break of half an hour, and we will meet again at 1:45 p.m. sharp.
Start before 5.
And start before 5 minutes.
All are requested after the break